Hello everyone and welcome to another class. I'm going to show you how to solve a multi-loop circuit. Well, here we have a circuit with 1, 2, 3, 4, 5, 6 resistors, one power supply, and the purpose is to find the currents on each loop. Well, first let's use the Kirchhoff node law, which is any current approaching a node equals the current or the currents leaving the node. So here, for example, we have I equals I2 plus I1 according to the expression here. Since we have only two loops, I'm going to adopt the clockwise rotation as my default rotation. And I can pick any point to start from and do the full loop or the full rotation in order to find the equation for each branch or each mesh. So here, for example, let's start with the power supply. When walking from the negative to positive, we have an elevation. So I have positive 10. Every time we have a drop in the voltage, we just put a negative symbol. Since this is the 5 ohms register, if I multiply the resistance times the current, I have the voltage. In this case, the voltage drop. So 5 times this I over here, look, is the voltage drop. Since I have a voltage drop, I will just put the negative sign in front of. Here we have another current, which is I1, I sub 1, or just I1. So I multiply 4 times I1. Look, I have the same direction. So this will be negative. Okay, so negative 4I1. And finally, finishing the loop number 1, we have 7 ohms times the current I. Okay, and this is negative because it is a voltage drop. So for the loop 1, this should be equals 0. Okay, because the energy is conserved. Well, let's see now for the loop number 2. I'm going to start with this register here. So we have 3 times I2, which is negative because it is a voltage drop. Coming to this R3, we have 8 times the same I2 because it's the same current on this branch. So negative I2. Finally, going to this register of 10 ohms, 10 times the current, which is still I2. Okay, since I start over here, I need to finish the loop, so I need to take this register into account. So look, the loop is clockwise. I have this current coming down, which is opposite to this loop direction. So this will be a raise. This will raise the voltage, or this will be a rise. And now I'm going to multiply 4 times I1, but the sign will be positive. Look, positive, because it is in the opposite direction. Okay, so this loop voltage the sum needs to be equal 0. Okay. Well, I know that I equals I1 plus I2. I can replace over here and here. When I do that for the loop number 1, I have this expression. Solving algebraically, I will have this final expression, which is the same of this equation here. So I just found one equation for the loop number 1. And for the loop number 2, I will just replace what it is needed. In this case, there is no need to replace anything because I have I2 and I1. There is no I. Okay, so doing the operations, we have 4I1 minus 21I2 equals 0. Well, to solve this system, you can use the technique you want. I'm going to use the addition. I multiply this equation number 2 by -4, so I can cancel this 16 and solve for I2, and I have this current for I2. And after plugging into the equation number 1, we find the I1, which is given by this expression here. Okay, easy to see. Well, so I have I1, I2, and of course I can calculate my I, which is 0.651 ampere or 651 milliampere. Well, you can solve this problem using a programming language. And of course, I'm going to run my simulator. Look, according to the simulator, this is the I, which is, as you can see, very, very close. Okay, the error is less than 10%. And this is my I1, and this is my I2. Let's see. I am saying that this is my I2, this is my I1. Okay, I1 is 0.547 ampere, which is a little bit close if you make the error calculation. Of course, look, we are using a simulator. A simulator will have some errors. Okay, it is not 100% perfect. Okay, and as you can see, everything is okay. If you want, you can just solve this linear system using a programming language. You can use Julia, for example. It is very easy to do that. I can just represent the equation like using the matrix. I have the matrix 16, 12, 16, 12, 4 and -21. 4 and -21. And the constants here, 10 and 0, as another array. So we have a two-dimensional array, which is a matrix, and here I have only a one-dimensional array, which is a vector. Okay, of course, this vector has two elements. Well, to solve this problem using this programming language, Julia, just use this backslash operator to find the solutions. In this case, two solutions, which is matching almost the values, I1 and I2 over here. Okay. Of course, if you want, you can just round using the round function. Okay, and specify the number of digits after the floating point. So this is the way it is. Well, here we have another circuit. Look, this circuit is composed by 1, 2, 3 loops. So it means that I will need to have to solve a linear system with 3 variables and 3 equations. Okay, each loop is an equation. So let's see, for example, how to set up the problem. Here we have the loop number 1, loop number 2, loop number 3. I'm using for all of them the same direction, clockwise direction. Look, this is the current crossing this register here, coming from here, which is I. This current will be divided into 2 currents, or it will be split into 2 different currents, I1 and I2. Okay, so this I2 crossing this register will split into 2 more currents, I4 and I3. Okay. After crossing this, we have the I2 here. Here we have I, and here I4, and so on. Okay, so let's see. I equals I1 plus I2. As you can see over here, I equals I2 plus I1. So currents arriving a node equals the currents leaving the node. Okay? In this case, I have just 1 current arriving and 2 currents leaving. Here I have I2 equals I4 plus I3. Since I2 equals I3 plus I4, I can rewrite I as I1 plus I3 plus I4. So I have 3 variables. Well, to do that, let's write the equation for the loop number 1. For the loop number 1, we have the power supply starting from here, negative to positive. It is a raise. Okay, and I have 10 volts, which is positive. Here we have a drop, 5 times I need to put the negative sign because it is a drop, a voltage drop. And here we have another current, not the same. Here I have I, and here I have I1. So since I'm using the same rotation direction, which is the clockwise, this will be a voltage drop, 4 times I1, negative. And here another drop, negative 7 times I. Okay, and of course I know that I is I1 plus I3 and I4. The same for this. Rearranging the terms, we have the first equation for the loop number 1. Okay, and let's see the loop number 2. The loop number 2, let me start with this voltage drop. So I have 3, negative 3 times I2, negative 3 I2. So going down, we have this register here, which is now using I3, because this current I2 will be divided into 2 currents, one I4 here and one I3 here. So negative 4 times I3, which is over here. And this will be I2, okay, because we have the 2 currents, I4 and I3, coming together to compose the original current, which is I2. So negative 10 times I2, because I have a voltage drop following the same direction. So negative 10 I2. But look, since I need to close the loop, I need to take into consideration this register, because I need to come over here. So this one is the last one to be calculated. But look, the loop is going up, this current is coming down. So this will be a voltage raise. Okay, so this will be 4 positive times I1 take a look here, positive 4 times I1. I have now all of these equals 0 to keep the law valid, Kirchhoff's law. Well, I can just plug in the I2, which is I3 plus I4 over here and here. So doing all the algebraic calculation, we have this final equation for the loop number 2. And finally, for the loop number 3, we have only 2 registers. Look, we have a voltage drop 8 times I4, which is negative here, and closing the loop, when I go up, this current is going down. So we have a raise, a voltage raise, because I'm following the loop and I just saw this current coming from the opposite direction. So this will be a raise. Okay? Every time you have opposite directions for the current and the way you follow your loop, you need to put a positive sign to this voltage drop. In this case, we have positive 4I3, which is over here, positive 4I3 equals 0. Okay, now I have a linear system with 3 equations, 3 variables, as you can see. I'm going to write over here 0, I1 for the loop number 3, for the third loop. And I can represent this as a matrix. Okay, so I have a 3 by 3 matrix, the variables and the constants over here. So I just write down the coefficients of each equation. Well, you can solve this using matrix and etc. Or you can just use software to do that. Well, in this case, I just use it again, Julia, writing down the coefficients, which is 16, 12, and 12, 16, 12, and 12, for negative 17, negative 13, here, and 0 for negative 8, here. 10, 0, 0 is the vector of constants. Using the same operator, which is this one, this is not a regular division. Internally, Julia is finding the inverse of the matrix and finding all the coefficients. And printing out, we have I1 equals 0.525, I3 equals 0.089, and I4 equals 0.045 ampere. Of course, we know that I2 equals I3 plus I4. This is the I2, and the I is I1 plus I2, which is this current. Okay. Well, let me just apply to the simulator. Look, and everything seems quite okay. Look, I equals 0.654 milliampere, 0.10 milliampere, which is almost close to this. And let's see the I2. I2 is 0.134, which is close. The value here in milliampere. Okay. This is approximately 89 milliampere. Look, we have over here something very close. And 45 milliampere for the I4. Okay. So I know this technique can be a little bit boring because you need to solve this system of linear equations. If you have for loop, a matrix 4 by 4, and so on. So in this case, we need to use, well, some computer programming language to help us to do this very quickly. Of course, you can do this manually, Okay, it is good if you want to remember how to do that, and etc. using the determinant and etc. Okay, but of course you can find the currents using another approach, like finding the equivalent resistance, finding the total current, which is this, and after using the voltage divider, and keep doing step by step until finding all the solution. Okay, well, I think that is all for the moment. Thank you for watching, and I see you in the next video. Bye.